Okay. Hi, students. Today we'll talk about combinatorics. Let me switch the screen to the presentation. I'm not sure if there is a TA with us, but I'll try to monitor the chat. Although that's a little challenging. But you can just unmute yourself and ask a question. You know, when I go over the slide and explain stuff, just ask.
One quick administrative question, if you don't mind, real quick. It's about I remember 2 days ago in the lecture you said that you were going to give us an estimate or like a visual estimate of where our grades are and how we are doing in the class.
Yeah, I'm preparing that. Yeah, so
by when?
Yeah, so maybe tonight I will send you something. I will send it out. I'm not sure. It takes time to compute this. This is like a lot of mess, so it just takes time.
Does that account for the curves as well, like the average of the class, if there is any curve as well?
No. All I will give you is like, here is the minimum passing grade based on the current stuff. And here is where you are in relation to that. That's it. So I say, okay, so I will say the minimum passing score is 66 and you have 69. The rest is up to you. Okay, you know the formula. So you know that, like, if you completely bump test 4, where your score is gonna be, right? So it's very clear. I will give you the formula, and I will give you, like, okay, right now you are at 75, and the passing grade is 66. Not grade, score, right? So okay. I guess you don't see it right now because I haven't emailed it, but once you see it, it's kind of yeah, okay, you know, let's post. So I will post it, and then anybody who has any question, like, what does this mean, what is this computing, you know, just post these on Piazza so we keep it in one place, and then whatever ambiguity there is, it's like a single place, and so you know, everything is clarified. How is that?
That sounds fine.
Somebody says no, dude, and I'm not really sure what they mean. Okay, maybe that was a comment to something I said. Don't worry about the professor. Okay, good. All right. Okay, so let's so yeah. Okay, so I was really try to be clear about the formula I use, but it's basically the same one that is that was set from the very beginning, right? And then you can also see, and there are some regrades that are not done. The only ones I see are on test 3, right, which is still not all of them are done. And of course, you know, you can ask again, you know, you might disagree with something, or you might not notice something. So then, but also you can use the same formula to compute what, you know, how it will affect your grade, right? Because it's a numerical calculation. So you know that if your delta is 5 points on test 3, then this will be, you know, 1.2 in the general score, right? And so forth. All right. Okay, let's go to the and in event, you know, the only purpose I had, so I guess I see, yes. So I see, because you are okay. So in my mind, there's only one reason about all of this, is that people who are in danger of failing can start, you know, spending some time trying to review things, so that to perform well on this remedial test, right? But I think that like most people already know whether or not they should be doing that, but okay, but at least they get like, okay, for sure you should be doing that. But I think that a lot of people, because it's like this special quarter, right? So some people are registered as pass no pass. And then apparently this Friday of next week, you can still like decide whether you want to do it for the grade or for no grade. And then, so you want to know like whether your grade is basically C or B or what. Yeah, okay, so I will give, oh no, I mean, this is just going to be such a mess, because everybody who is like on a little border is going to be like completely trying to like squeeze out some point on some homework, you know. That will be a complete administrative and logistical nightmare. All right, but I guess you want to know where you are, so I mean, I will give like an orientational, like, you know, like about this here is C, and about this here is B, and about this here is A. Yeah, so I will not commit to exact stuff, but I will tell you approximately where this goes. Whoa, okay, okay, so it's tough. Tell me what's okay. All right, okay, so anyway, let's just postpone this, and if you don't have you know, clear questions to this, I mean, and by all means, you know, post it on Piazza. Like if you think this is something is not sort of confusing about this, let me know, because there something might be, you know, and I don't quite see it. I don't see everything you see, you know. All right, let's go to this stuff, because we have a lot of stuff to do. All right, so okay, so we ended up with these examples of counting, right? Like where like a massive amount of examples was basically from poker, right? So suddenly now we have to be all learn hazard games and you know, drink whiskey and smoke and play poker. All right, but before you do that, you start like learn how to count this stuff so that you know, you play it well. All right, so some other examples, and this is actually a general thing. It's called counting by complement, and the idea, very simple one, is that it's sometimes easier when you're asked count something, count some set. It's actually easier to count the complement of this set. If you think of, you know, you have to count some elements with some constraint. Okay, count those that satisfy the exact opposite constraint, right? That all those that do not satisfy this. Perhaps it's easier. So there are certain problems where this is true, and I will just give you examples of some. Okay, so you ask, okay, a poker card, how many possible cards have exactly one card of club suit, right? Well, how would you compute this? So, well, let's pick all the possibilities of picking this one club card, right? So basically choose the rank, because the suit is already chosen, and then choose the remaining 4 from all the rest, right? So the 3 suits. Okay, so this one is 13 choices, and this one is 39 choose 4, because there's 39 of the other suits, and you have to choose 4 cards out of them, right? The constraint is that the other 4 are not a club, right? So this is your total, right? But let's say that I ask you, how many 5 cards have at least one club? Okay, so now, okay, you can do this in the following way. So, you know, count all those that have exactly one club, the way we did, right? Now you can do it the same, basically, count all those have 2 clubs. So what is this now? You choose 2 out of 13 of club cards, times you choose 3 out of 39, right? Which is the remaining suit. And here, choose 3 clubs. Okay, so you choose 3 out of 13 clubs, and then you choose 2 out of 39. All right, and so forth for 4, and so forth for 5. But it's like a pretty hairy formula, right? Like it's a summation of 5 things, each of them somewhat complicated. Okay, is there a faster way to do this? Yes, complement. So instead of counting all cards that have 5, at least 1 club, let's count the whole universe, so all cards at all, right? All possible hands, and all those hands that have no clubs. And that's much simpler, right? Because the remaining are those that are all possible. It's some hand, but not in this set, right? So it's not one that doesn't have any clubs. So it has some clubs. Well, that's what you were supposed to count, right? So and why? So this, we would do this if computing this set is somehow complex, and you say, okay, how about the complement? Complement is super easy. Okay, good. So I'm done. Okay. So 5 cards. So okay, so I take all 5 card hands, and I subtract 5 card hands that have no clubs, that violate this constraint, right? That are in the complement of the set. So this is 52 choose 5, right? No constraints at all. And this is 39 choose 5, because I'm choosing all 5 in the remaining suits, right? In the remaining 3 suits. So that was much simpler than this whole summation. Now they have to equal, right? So this whole summation must be equal to this. We'll come back to stuff like that in the last lecture. There are certain equalities and rules among the stuff, and that is one. Okay, it's basically it's a case of something called binomial theorem. All right. Here is another example. So you are choosing strings, 8 strings of length 8 over certain alphabet. And let's say you are given a constraint that there must be at least 1 A. If you were told that there is exactly 1 A, well, that's simple. You just have to choose position in this string for the A. There are 8 choices. And the remaining 7 digits are unconstrained, but from limited alphabet. So there's 2 to the 7 possibilities, right? Because the alphabet is 2 bits, B and C, 2 characters. And there are 7 positions you have to make these choices, right? Independent choices, so it's 2 to the 7. So it's 8 times 2 to the 7, easy. But what about at least 1 A? Now you have to do this for 2 A's, 3 A's, 4 A's, right? But the complement is much simpler. Count all of them, which is 3 to the 8, and subtract those that have no A, which is 2 to the 8, right? Because it's a limited alphabet. So boom, a much simpler formula. And of course they are equal, and that's the kind of stuff that we'll come back to. All right, here's another funny counting problem, counting permutations with repetitions. So permutation again was that you permuted the set, right? So you had a set of some fixed elements, and you were just concerned about the order between them, right? You were reordering them. But what does it mean to reorder and repeat?
I'm sorry, quick question real quickly. Can you go back to the previous slide? Yeah, so when you were talking about the set of the length of strings over ABC, just to clarify, because like you have 3 strings. Okay.
Yeah.
I see.
Right, because this alphabet has 3 digits, and there's 8 times you choose the digit. And here the alphabet now has only 2 digits, and again, you're making 8 choices of them, right? Because it's a string of length 8. Okay.
Okay, that makes sense. Yes.
Okay. All right. So let's put this problem here in this spectrum of what we know, right? So we know how to count ordered sequences where there's repeats are allowed, right? So you're taking from some alphabet and you taking an ordered sequence, right? And you can, well, if you chose some character for first, you can choose the same character for the second, and so forth, right? So this is how many there are. If you don't have repeats, then your choices every time are reduced, right? So this is the formula. So these are permutations, or n permutations out of the, actually this should be t permutations, sorry, because there is a t here. And if what you're choosing is an unordered thing, right? So it's a set, then okay, then it's a you know, this a choose t expression, right? So the question here is like, what if you had an ordered you were choosing an ordered sequence, but you are somewhere in between these. So you're allowed some repeats, but in fact there is a fixed number of repeats you have to do. Okay, here's what I mean by that. So let's say you're permuting 3 unique letters, BAD, right? So there is 6 possible permutation. All right. It's n factorial if there is n letters. But what if some of these letters repeat? Okay, so that's what I mean, that this is an ordered sequence. Here's your choice, but there is a fixed budget of Ds that you have to use, right? So basically, and there is no difference between these 2 Ds. So permuting them inside would not constitute a different choice. Okay, so there is only these many ways to permute these letters, right? So what is it in general? Okay, because like, okay, this was simple. There was 3 letters and you had only 1 of them repeat. So, okay, so you can figure it out that it's basically, there's 3. But what's the general formula? You have n letters and some of them repeat. Okay, so let's take a Mississippi, because it's a good one, has a lot of repeats, right? So it has 11 letters and 4 of them are I's, right? Right here, spread around nicely. 4 of them are S's, grouped here. There is 2 P's, and then there is 1 M. How many ways can you reorder? Basically, how many different words can you write using this bag of letters? Well, you can go like this. I have 11 placements, right? I have 11 places where I have to put a letter. Let's choose the places where I's go. So I have, it's 11 choose 4, because out of 11, I choose 4 places for the I's. Now, once I'm done with those, how many places do I have left? 11 minus 4, so 7 places. And I have to choose, let's say, my next choice is where to put S's. So out of the remaining 7, I choose 4 that I'm placing S's in, right? So 7 choose 4. Continuing, how many spaces do I have left? 3, right? Because I had 7 now, and I occupied 4 with S's, so 3 left. And now I choose 2 of them for P's, and then for M, I don't have any choice, right? I already fixed 10 spaces. So M goes into single empty space left. Of course, you can ask, like, who told you to choose I's first? Why didn't I choose M first? I could. These numbers would be different, but the total better not change, right? Because, well, it should still give me exactly the number of words that I can write using letters that Mississippi is made of. So why is that true? Okay, let's see what this number really corresponds to. Okay, so here is this thing again, and now if I compute this, right? So what is 11 choose 4? It's 11 factorial over 4 factorial times 7 factorial. The next guy is 7 factorial over 4 factorial 3. Note that there is a repeat between this and this, and between this and that. And it is not coincidental because the number here is exactly the difference between these two, right? Because I started with 11 places and I chose first to occupy some 4. So I'm left with 7, but this thing is going to have exactly the same 7 in the denominator, 7 factorial. So it will cancel. So basically after canceling these and these, what I'm left with is this. And look, 4, 4, 2, 4, 4, 2. There is a hidden 1 factorial right here, but 1 factorial is 1, so it doesn't have to be written, right? Well, perhaps this doesn't convince you that all the orderings here that I will choose to it will come out with exactly the same, but they will, right? I mean, right? Because if I reorder this and say let's choose 2 first, I'm going to have 11 choose 2, which will be 11 factorial over 2 factorial times with 9 factorial in the bottom, but the next choice will be out of 9 places. So I'll have 9 factorial on top. So instead of 7 factorial canceling, I will have a 9 factorial canceling. So the same thing will work, and you will get this answer no matter what the order in which you do these things, right? Here is another way to look at it. So anyway, so how many you order? Well, it's permutations of the whole thing divided by permutations of the i's, the sort of internal invisible permutations of i's, divided by internal invisible permutations of s's, and then permutations of p's. What is going on? Why the answer seems to be that I first permute all of these letters pretending that they are the same, because sorry, that they're all unique, opposite. That they're all unique, right? Because if these were the unique 11 letters, this would be the answer for how many permutations there are. And then I somehow cross out these invisible permutations of s's, p's, and i's. Well, this is exactly what's going on. Okay, so how many permutations are there of a string n, of n characters? But these characters have characters C1, C2, to CK, where k is smaller than n. And you have R1 copies of C1, R2 copies of C2, etc. So these copies have to sum up to n. And the general answer is this. So Mississippi example was that there was the total number of these characters was 11, and the multiplicity of the first character I was 4. The multiplicity of the next character S R2 was 4, and the multiplicity of P was 2. Right. So this is a special case of this general formula. But what is really happening is that this general formula is true because it's an application of a K to 1 rule. It's a K to 1 rule where K is this factorial expression. Okay, it's the permutations of R1 elements times permutations of R2 times. Okay, why is this? Because here is a function that takes any permutation on all, think of this as Scrabble, and the characters M, I, S, S, I, S, S, okay, are all Scrabble pieces. There's 11 pieces. And if you wanted, you could write numbers of them, 1, 2, 3, 4 to 11. Now they become all unique. right? Each of them is unique. It's numbered. So even two S's are different. One S has index 3, the other has index 6. Okay, so now if I mark them individually, I will have total number of permutations will be n factorial. There is n factorial ways to permute these n Scrabble blocks, each of them unique, independent, right? But I can assign to all such permutations a word that comes out, and there will be collisions because the two permutations, which are different as permutations of 11 blocks, but they come out to the same word, collide in this function, right? And now what are the number of pre-images of everything here, of a word like Mississippi? Well, it's all those permutations of blocks that create Mississippi. So basically, I can take Mississippi and permute all S's, and I still get Mississippi. And I can permute, so that would be this number of collisions. And independently, I permute all I's, and I'll have this number. For each of these collisions, I create this many more. So this is the total number of collisions that you have when you do this mapping between thinking of these permutations as Scrabble blocks, where they're all unique, and thinking of them as permutations of letters, where now the fact that all S's were different is now stops being a fact. They are now mapped to the same, creating collisions, exactly this many. So it's a k-to-1 function, which this is the k, which explains this formula, right? Because you just count those and you divide by how many collisions this function creates. Okay. Question. So I think it's a super nice case of a k-to-1 really giving you something, like really allowing you to do stuff. Okay. So, okay, so some examples. So you have alphabet, and you're told you have to use 6 A's, 3 B's, 2 C's, 7 D's. That is exactly like this Mississippi. Now it's just that with different multiplicities of these letters, right? So now you just have to think, okay, how many letters I have in total? What's the length of the whole thing? Well, it's the sum of the number of these individual letters, right? And again, I can look at this as an n-to-1 rule, right? So I basically I can write these on the individual Scrabble blocks. Then there's 18 of these blocks. I permute them anyway. There's 18 factorial permutations, right? And then I divide by all the reorderings of A's. There's 6 factorial. Reorderings of B's, which is 3 factorial. Reorderings of C's and reorderings of D's, right? I divide these out because they create collisions. When I move from thinking of this as individual Scrabble blocks to thinking of them as words that come out, where all the A's now are identical. So I have to remove 6 factorial. By remove, I don't mean subtract, I mean divide by, right? Because the space of all these possibilities is just slashed by the 6 factorial factor. Okay. So here is how many students do you have? Can we go over bijection questions? Somebody's asking. Well, go ahead. Like this is, oh no, this is the k-to-1. I don't know if I have, oh, so for homework, yes, this is the tough one. Yeah, this is the toughest part in some sense on the homework, like figure out those bijections between sets, so that to allow you to count. But let's do this at the end, right? When I'm done with this stuff, like whoever wants to stick around, we can talk about this, maybe go over some examples. Sorry, that was a chat question. If somebody watches this on YouTube, then they don't get to see the chat question. It was about the homework bijection examples. All right, let's come back to this thing. How many ways to assign 20 different tasks to 5 distinct students, such that each student gets the same number of tasks? So basically, you can think of them, the tasks are, so you know that because there's 20 tasks with 5 students and they have to get equal, so everybody gets 4 jobs, right? 4 tasks. And here is one way I can represent this process, right? It's sequences of length 20 with 4 1s, 4 2s, 4 3s, 4 4s, 4 5s. These are these are basically student tokens that are going to be placed in a different job, right? And now so my jobs, there's 20 jobs. Okay, so let's think of them as places. Okay, and there's 20 tokens I can place in these 20 places. 4 tokens are labeled 1, 4 tokens are labeled 2, 4 3, 4 5, 4 4 4 5, right? The token, these numbers mean they are student IDs. So when I place these tokens, I will think of this way: the first how many jobs there are? 20 jobs, right? So the first placement is who gets job number 1. The second one is who gets job number 2, etc. Now, the tokens are indistinguishable, right? Because if the 4 tokens marked 1, they all signify the same thing, that the first student gets that job. So basically, the number of these assignments is the number of strings of length 20 made of these characters. Each string made of these characters that have, exactly this many characters, right, of each type, will correspond to a different assignment of jobs. So that's a way to look at this. There's a word of length 20 with these constraints on characters that have to appear, right? So it's a case of the same things that we've seen before, right? Again, you can think of this from the scratch, which is permute all of them as if they were all unique, and then stop thinking of them as unique, realize that 4 ones are the same, but what is the factor that you have to remove? It's 4 factorial, because that's how many permutations of these are going to create collisions when you go from thinking of them as unique to thinking of them as the same. All ones, all token ones are actually the same. So that would be the final answer. Okay. Here's another one. So you have 10 cookies, 10 kids, and you want to give 1 cookie to every child. The sequence of job assigning matters. Well, okay, so somebody has asked, does the sequence of job assigning matters? So okay, so the way I represented this assignment was with a string of length 20. That first assignment tells me which student gets the first job. The second character in the string tells me which student gets the second job, and so forth. So the 20th character is which student gets the job number 20. Okay, so that's the meaning, that's the interpretation of the string. So now each such string tells you about different assignment of jobs to students, right? And what strings are possible? Well, what are the characters? Tokens from 1 to 5, representing 5 different students. And are there any constraints on the tokens? You know, can I not use some token at all? Or can I have one token, everything? Yes, the constraint is that every token has to appear the same number of times. And because there are 5 different tokens, so this means they have to each appear 4 times. So basically now I have to make the string out of 4 tokens of type 1, 4 tokens of type 2, etc. Right? So it's exactly like this Mississippi case, right? With the long, the string, the length is 20, and I have 4 M's, 4 I's, 4 P's, 4 S's, and 4 A's, representing 5 different students. Now, you can maybe think of this assignment in some completely different way. If you do, post it on Piazza. You know, if you have some completely different way of counting this, or you are wondering, why can't I count this way? Don't think of this as a string. Think of instead some completely different way, like, the students are strings or something else, right? So a student asked, shouldn't we do choose 4, 20 choose 4, and then 16 choose 2? Yes, you can, and you're gonna come with this. Very good. Yes. So everybody, what the student said is, yeah. So this for people watching on YouTube, somebody said, okay, an alternative way of counting would be pick 4 places for digit 1, so that's 20 choose 4. Then 2 places for digit 2, that's 16 choose 2, choose 4. Then the next one will be 12 choose 4, then 8 choose 4, and then 4 choose 4, which is 1. It will come out to the same number numerically. So do you no? Because it doesn't matter. That's the same thing. Yeah. So you can write either one. They actually come out to the same. I mean, this one is simpler. It's faster to state, but the other one, oh, it's not much harder. Yes. So yes, exercise. Convince yourself that these 2 ways of counting are come out with the same. Okay. And it's a general thing for this, right? It's is this the same as n choose 4 1 times n minus 4 1 choose R2 times n minus R1 plus R2 choose R3, etc. And yes, it is the same. That is exactly what was happening here, right? So that's what we started, and we came out with this formula. So that these 2 are the same processes. Well, okay, you already have it here, but it's true in general, right? Okay. So kids and cookies, right? So now you have 10 kids, 10 cookies. The cookies are fixed, right? So it's basically choosing. My selection is I have 10 places, a string of length 10. Each position tells me which cookie. A character at position I tells me which cookie, what cookie kid I gets. Right, so the first position will be the cookie that the first kid gets. Second position cookie that the second kid gets, etc. And I'm placing these letters among these positions. So that's the formula, right? All right. Okay. Well, what if I had more objects to place to kids, right? I mean, okay, and actually, why there were 2 ones? Shouldn't have one having 2. Okay, what's the question? Yes. This is a typo, right? 3 plus 1 plus 4 plus 1 is not equal to 10. Typo here. There's a 2 here. Sorry. Or there's a 2 here. Yeah. Yes, yes, that is a typo. Thank you. Thank you. All right. So now, okay, what if we have, instead of 10 cookies, we have 20, right? So 20 books, and each kid gets the same number. Okay. So how could I count now? So, okay, so now let's think of them, let's separate, kids and cookies, right? And how about this way? Here is, my tokens are kids, just like this is basically like students and tasks, right? This is the kids, the kid tokens. 2 of them are 0 for first kid, 2 of them are 1 for the second kid, etc. And now I place them. My string has 20 length 20, and the first character will tell me which kid gets the first book. The second character will tell me where the second book went. Okay, depending on the token placed in the second place, that will be the kid to which the second book is given, right? So it's number of strings that you can form using these characters. 20 characters, but grouped into groups of 10, each of them repeats twice. So that will be the answer, right? So again, like, how do you know? Okay, should you think of strings of, the number of kids here, or should you think of strings, the number of books? Who are you assigning to whom? What are the constraints? Well, try to do it one way, see if you can, if it resembles some problem or it's hard, and then switch. Try to think of it the other way, and maybe now it will be easy. Just there's no better way to just try. I mean, of course, as you do these things, they will be like, okay, this is just like that one. Before you start, there is really no other way except that this is some assignment. How can I represent it? Is it perhaps with a string? And it's all like about like different letters coming and what the alphabet is and are the constraints. And or perhaps it's a set, or let's switch. Let's think of, right? Unfortunately, there's no fixed thing except of try and be able to switch if it doesn't go well, if it seems complex, too complex. And now if you how many ways to distribute 20 different quizzes without restrictions, right, on the number? Well, so this has a much simpler answer, right? It's I just have a string of 20, and I can write any character at every position of the string, right? And my alphabet is 10 characters. So it's basically the number of decimal strings of length 20. Okay, here is another problem type. Counting subsets with multisets of multiset subsets. All right, so these are like sets with repetitions. Now that's crazy thing, because a set is precisely like, there is no notion of repetition in a set, because like a set that has 3 elements, all of which are equal to 1, is really a set of 1 element, right? But hence the notion of multiset. Okay, so in the spectrum of things, where is this thing placed? It's kind of here. So we can think of different ways of choosing ordered objects. Okay, where position matters, and ask, okay, the basic switch is, okay, these objects are filled up with certain characters. So what's the alphabet? And how many are them picking? Well, that's the length of the sequence. But we're gonna basic switches like can you repeat in which case you're here or can you not. Now with the unordered sets, right? Like we understand that there is no repeat, but what if the set was well, it contains this it contained copies of sort of identical element, but it still mattered whether I'm taking a given element once or I'm taking it twice. So that's the notion of a multiset. Okay, let me first like explain what that is, right? So multiset is a kind of a set where the same thing can appear several times, but the order does not matter. Okay, so in other words, this is a multiset. It has a single 1, 3 2s, single 3, single 4, single 5, and 2 7s. As a set, it would be these two multisets would be the same, right? Because oh, well, actually, because it's unordered, so these two are the same multisets. But this guy, which differs from those two, because the multiplicity of 2 from 3 2s it went to 2 2s. It's a different multiset because the multiplicity of some character changed. As sets, all of these are the same, right? So if you think of it as set, then it's a set of just 5 elements: 1, 2, 3, 4, 5, and 7. At least that's 6 characters. Okay, 6 elements. But when I write such a thing, I mean a multiset. It's still not the same thing as a sequence, right? Because these two, if I think of them as sequences, then they would be different because the order didn't change, right? But when I think of them as multisets, where the only thing is what are the elements and what are the cardinality, like multiplicity of the given element, then these two are the same. Okay, so here is one example, okay, of where this comes up. Okay, so say you're purchasing 12 donuts, and there's only 4 types. So it's sort of like you're making string out of 4 characters, C, G, J, and M. Okay, and you have to make a string that has 12 characters. Okay, because you're buying 12 donuts, but it's not a string at all, because it doesn't matter what order they are both. You're buying them in a bag. You're putting all these donuts in a bag. You can shake the bag. It doesn't matter what order you put them in. So it's not really a string either. That's the case of the Mississippi stuff, right? Where the order mattered. But it's similar to Mississippi, as in the same character, every occurrence of the same character, like the same chocolate character, is the same. There is no difference between chocolate donut number 1 and chocolate donut number 2. They're both, if I fill my bag with chocolate donuts only, that's one choice. It doesn't matter, if the store owner, knew that, oh, this was like my chocolate donuts that I baked first, and this is my chocolate donuts that I baked second, and so forth. So he knew what the order was. But the customer who put them all in the bag, for her, this choice is identical. It's all chocolate. So, and let's assume that there is no limits on this. So the customer can pick 12 of chocolate, 12 of glaze, 12 of jelly, 12 of maple. Yes. So any possibility of these choices are the same. So how many ways are there to select this? And basically, the only thing that matters is how many chocolates did you choose, and how many glaze, and how many jelly, and how many maple. Whatever these numbers are, right? So let's say you took A of chocolate, B of glaze, C of jelly. Well, then maple, you have no choice, right? It has to be 12 minus A plus B plus C. But what are the possibilities of A by B, C, right? Well, you can list them, right? You can make like a three-dimensional thing where the solution is fully determined by just the choice of A, B, C. Number of chocolate, number of glaze, number of jelly, right? And how many possibilities are? Well, for A, you can go anyway between 0, no chocolate, to 12, all chocolate. And then for B, well, it will now depend on A, right? The number of choices is sort of a function of what A was. And for C, the number of choices is what will the. So this will get complicated because of this dependence. Okay. Okay. So now let's see what the possibilities. Oh, somebody says whether this is possibly 48 choose 12. So you have 48 donuts and you choose 12 of them. No, because think of, so that means that you have 48 unique things and you're choosing 12 out of them. No, because that would mean that all 12 chocolate donuts are unique. So whether you're choosing first and second chocolate donut versus 11th and 12th chocolate donut, it somehow constitutes a different answer, right? So where would your answer be 48 choose 2, where you have 48 unique things, like cards in the deck, where each card is separate, right? There's 52 of them, okay, but it's the same type of thing. I choose a hand, each of them is unique. Here I choose a hand of donuts, 12, but these choices from which I'm choosing are not all are unique. 12 chocolate donuts are all identical. 12 glazed ones are identical. It's as if I chose cards and then forgot what the rank was and only counted soup. And basically asked you, if you were figure blind, rank blind, and the only thing you see about the card is its soup, how many choices do you have? And now it becomes complex, because if you choose 3 chocolate ones, well, you can remove the permutations of internal permutations of chocolate. That's you slash down by 3 factorial. But that depended whether you took 3 of them or you took 4 of them. So every choice seems to be like related in a different way, right? So now it gets really hairy. 15 choose 3. Yes. Okay. Yes. 15 choose 3. Okay. So let's see why. Why is it not 12 to the 4? Somebody says, right? So you have 12 donuts and you're choosing 4. No, you're choosing 4. In what sense are you choosing 4? Because there's 4 suits. Okay, right. Four flavors. Yes. So you have a string of 12. No. 12 to the 4. You know what? I don't know why 12 to the 4. Okay. I think we have to, why would somebody think it's 12 to the 4? Maybe there is a simple way to think of this, but I just don't see it, right? It doesn't mean anything. It's often like that with these things. I just don't see the way you count, and I cannot tell you why it's wrong. Okay. All right. So people can pipe in, but in the absence of that, I would just tell you, okay, how to count this. So you have these. So here is my sample selection, right? Like 12 characters, 3 C's, 1 G, 5 or 6 J's, and 2 M's. I will encode them like this. I will encode them using binary code words, which is well, how come I encode them just with zeros and ones? But here's the way. What I will count is where is the division between flavors. So my binary string will have zeros wherever there is. Okay, so first what I do is I give these flavors names and I order them in some unique order. So like from the least alphabetical order, right? And these zeros will tell me how many donuts am I taking of the first flavor, of the first type. If there is a 0, it means I'm picking some donut of the first type. If there is a next 0, I'm again picking. If there is a 1, I'm switching the flavor. And I move on to the next alphabetical flavor. That's the encoding that, you know, some committee of superanal friends can give this girl who goes to the store and orders donut selection. They could use this bit string to encode her selection using this algorithm. Order the donuts in alphabetical order, type of donuts in alphabetical order, and the bits we are telling you mean as long as there's zeros, you're picking donuts into the bag from the first flavor. If you see a 1, you switch the flavor to the next one and repeat, recurse, right? So now she's at the next flavor and she sees a 1, a 0. This means pick a donut. Next bit is 1, means switch a flavor. So move on to the next flavor. You see a bunch of zeros. She's just following this algorithm, this encoding. She's just picking the next flavor, donuts. She encounters a 1, she switches, and then she's left with the highest ordered flavor. She picks, there's a bunch of zeros, right? So she picks them. This type of string will encode a selection, but there is constraint on this string. What is the constraint? It has exactly 3 ones, because the only constraint on these bit strings are how many times are you switching flavor? And we are going to say that number of flavors minus 1. And well, you can ask, well, what if I just choose all chocolates? It will be encoded by this bit string with all the ones bunched at the end. All this is a 0, 0, zeros, because you're picking the first flavor all the time. Now you're done. You pick 12. And now you have this bunch of useless ones, which encode flavor switches, which will do nothing, but whatever. Yeah, that's a valid encoding. What if I choose only M's, maple, right? So I have a bunch of flavor switches once at the beginning and then all zeros, right? So that's the encoding. And now you can see that how many bit strings of these there are. 15 choose 3, right? So again, this is the encoding that I just walked over, right? The zeros mean the algorithm, this robot picks the donut of the current flavor. The 1 means it's a flavor switch, flavor increment. And that's it. You gave the robot exact instructions, right? And can you encode every donut selection using such a bit string? Yes, right? So you can just sort of look at the examples and basically see that however you write this, it will be encodable in this fashion, right? Because indeed, like any selection of donuts can be encoded. Pick, pick, pick. How many picks there are? 12. And switch from flavor to flavor. How many switches? 3. Yes. So, you know, so here are the examples of some of these encodings that maybe are not immediate, but you know, here are the encodings for these kind of selections, right? So somebody gives this formula that does not look correct. It does not look correct. So this might get lost in the chat. So maybe post it on Piazza if you believe in your formula, and then we can all think like whether that way of counting it is correct too. This is not a bad idea, you know, like it's very, very natural. And indeed, for many of these things, there is a different way of counting. Perhaps it's not easier, perhaps it's equivalently difficult or easy, perhaps it's harder, but it's either correct or incorrect. And if it is incorrect, then it's a good exercise to think like why. And if it is correct, it's even better, like why. Two ways of counting this are possible. That's a very good stuff. So by all means, I encourage you to to hash it out the best way. Okay, post on that, like here is an alternative way of counting, what's wrong with it? Or like, does it come out with the same answer? I cannot tell. Could anybody explain why? Okay, so so I have 15 bits with these constraints. So the choice is 15 choose 3, right? Because it's just a position for ones. I have to have fixed number of ones, 3 of them, and I just choose their positions. Every position, every different choice of positions will encode different selection, right? Well, I'm going over this over and over on a bunch of slides, but it's all the same. And here's some examples of like, well, how to read these encodings, but we have been going over those, right? So, for example, this one is the all J's, and so because it is like choosing a bit string of length. I said 12 choose 3. Okay, no, it's 15 choose 3. Maybe I said that. I don't remember. Because these bit strings have length 15. There is 12 zeros and 3 ones. So it's the number of donuts you choose plus the number of type switches you can have, which is the number of donut types minus 1. So here is the general formula, right? Well, you have 12 donuts with 4 varieties. That means 12 zeros and 3 ones. So this is the 15 choose 3 is the answer, right? Because that's how many of these bit strings of length 15 with exactly 3 ones there are. And more general, if you have n items, like n donuts that you're buying, and m varieties of these items, so m types, then the bit strings that encode a selection have n zeros for pick an item. You have to do it n times, and m-1 extra characters for these type switches, for switch from first variety to the next, to the next, to the next. So there's going to be m-1 of these increments. So that's the total number of the string, and how many, the only things that differs between them are the placement of these increment characters, which are the ones. So that's m-1 of those. This formula, by the way, is still true, like, for example, if in a kind of uncharacteristic situations, like, for example, you're choosing a bunch of many things out of a small number of varieties. Well, that's not uncharacteristic. That is the donut example. But what if you go to the store and you're choosing only, say you're this weird person who eats only 3 donuts. You're just buying it for yourself, I guess, for you. But there is like a million of varieties, right? Like there's 15 different varieties. Now what? Now n is small, oh, this is messed up, right? So it's n is rather, so obviously I meant here the opposite, right? So anyway, you see what I mean. Where the number of items is much smaller, it's smaller than the number of varieties. Well, the same thing works. It doesn't matter that you have only few zeros and a huge bunch of ones, which are the type switches. But still the same algorithm works. And therefore, it's the same counting, the same way to count these. And this is also not a problem, that you have, the same number of zeros, and the context switch is basically one less, right? Because the number of varieties is exactly the same as the number of donuts you pick. All right. Okay, so let's see. Okay, so there's 75 types of taffy, and you select 12. Right. So that's the case where you have this huge bit string that has 12 plus 75 minus 1 characters, and 75 minus 1 are ones. So it's this summation, right? So it's 75 plus 12 minus 1, 86, with 12 zeros and 74 ones, right? So this is the way to count, right? So this, if you plug in this formula, it will be 86 to 74, but 86 to 74 is the same as 86 to 12. Say you have there's 4 types of computers, and there's a cluster that has 25 computers. And how many? Let's say that a cluster is a given type. Is a choice of cluster means choice of first type computers, number of first type computers, number of second type computers, number of third type computers, right? So so it's a selection of 25 donuts out of 4 flavors. Yeah, so it's this, right? Because number of flavors minus 1, and it's 25 donuts plus 3, number of flavors minus 1. Okay. What time is this now? Okay. Okay, so let me continue. Okay, so I might go a little longer. It's 1:37 right now. To basically generalize this, what we're talking about, into this sort of general problem type, balls into bins. So if you conceptualize the assignment type of problem as I have some balls and I have some bins, and I'm placing these balls into these bins, and a bunch of things happen when you say, well, how about each bin can only accept a single ball? Or are the balls the same? Or are all balls different, tagged by different identifiers? Are perhaps balls, just colored? So there is a certain number of yellow balls, certain number of green balls, and so forth. So here is now this is a very different way to, I mean, it's a new way of thinking of this, like we were thinking before, of taking either sequences or taking sets and looking at different variants of this, right? Now let's switch and think of these as balls into bins, but there will be correspondence between these. And maybe some problem will look easy now that looked hard before. There could be the opposite, that some super easy, obvious things that you knew, now it will somehow look more complicated, but okay, that doesn't matter, right? Like, so, all right. No, the point is to make certain things look possible, and to have a unifying way of thinking of this. How many ways to put n identical balls into two m bins? And let's say you have a constraint that, okay, so the bins are all different, right? The boxes into which you're placing things are different, but all balls are the same. So there is no notion of ball number 1, ball number 2. It's just the count. How many balls came into first bin? How many balls came into second bin? That's the only thing that matters. But let's say you have a constraint that actually a bin can only either have a ball at all and that it stops, cannot accept any further, or it doesn't have one. And well, that's m choose n, right? Because if you have n balls, then you're basically choosing n positions out of the m bins into which some ball is going to go. 2 balls cannot go in the same bin, so each ball has to occupy a bin. So n bins will be occupied. And the only selection is which bins are occupied and which bins are not. So it's m choose n, right? It's choosing the number of bit strings of length n, which has exactly length m, which has exactly n ones. Okay, how about how about the same constraint, okay, only 1 ball per bin maximum, but now every ball is different. So the balls are numbered, okay? So now the choice is, well, I could think of this way. First, I choose which bin is occupied. And secondly, I do what? Well, I stop thinking of the balls as all identical, right? I label the balls, which basically means permute them. So it's this many times n factorial. Well, that was how we arrived. So we actually did the opposite process, right? We started with this and created that as a function of this. Now it's the other way. I get the number of n permutations out of n element string by choosing n out of m and then permuting the balls into chosen n positions. So multiplying by n factorial. That's what I get. Now, what was this number? It was number of n string, n long strings made of characters which came from a set of m characters, right? This was our way of thinking of what this is. The number of n permutations in an m element set. Is that what happened with balls and bins? Well, perhaps. So let's think of them the other way, that so if we were thinking our traditional way of this, right? Then what would we do? I'm forming a string of length n out of character alphabet whose characters are from between 1 and m. So let's say I chose certain characters. So these characters are bins. And if I choose a certain bin as the first element in the n long string, that's the bin where the first ball went. The second character in this n long string will be the bin where the second ball went, but it has to be a different bin, right? So in other words, I'm choosing from a restricted alphabet which doesn't have this first bin in it. That's exactly the process of choosing n permutation out of a set with m characters. So it is just two different ways of thinking of the same process, right? And no surprise that it gives you the same answer, because by all means you should arrive at these two answers if both ways of counting are correct. But you represented this, you thought of this in two different ways to arrive at this. Okay, so far so good. We're seeing basically the different ways of thinking of stuff we already know, of stuff we already seen, where it was interpreted as not balls into bins, but it was always interpreted as a sequence taken of a fixed length from a certain alphabet, or a set of a fixed cardinality out of, yeah, a subset of fixed cardinality out of a set of m characters. But now we are thinking of this differently and yet arriving with this familiar concept, right? Okay, let's remove these constraints. So think of, let's do this one first. You're choosing, placing n different balls into these bins, but there is now no constraint over how many. So I can no longer think of this as like, I first choose the bins the way I chose here, and then I ordered the balls within them, which gave me this. And because the balls can fit into the same bin, right? But this is a super simple one. Every ball, there is n balls placed, and each of them makes m choice, one choice out of m, right? Has basically m choices for each one independently because there is no restriction. So this is simply m to the n, right? You made n choices, each of them was 1 out of m. And indeed, every assignment of these can be written as a string of length n, where every character is unconstrained from this alphabet of size m, right? You know, the way I read the string is that the first character tells me where the first ball went, the second character where the second ball went, etc. Okay, so how about identical balls into bins without constraint? So the only thing that matters is the multiplicity of how many balls went into first bin, how many balls went to the second bin, how many balls into the third bin. Does this remind you of something? You have a fixed budget of balls, n of them, and you have these bins, and the only thing is how many balls you're placing. What other process we have seen like this? Type or say? Mn plus, yes, it is exactly the donut selection, right? It is exactly the donut selection. The bins are the flavors. When you're selecting donuts, the bins, you're throwing balls into these bins. The bins are the flavors. How many balls you have? 12. It's the 12 donuts. It's the 12 choices of flavor. You're throwing these balls into the 4 flavor bins: chocolate, jelly, whatever that was, right? Glazed, jelly, maple. Yeah, that's what it was. You threw 12 balls into 4 bins. Each way of throw, each multiplicity of these would constitute a different donut flavor choice, right? So it is exactly the case of that stuff. Oh, why do I have this? Okay, I don't know. So here, okay. Well, I guess I just go through this. Sorry, I forgot. I think I didn't even look until this point to tell you the truth. Sorry about that. I mean, yes. So I was busy trying to get your grades and dealing with the regrades and so on and so forth. Sorry about this. Okay. So again, this is basically what I said, right? Like it's the selection is like this donut selection. Where is my conclusion from this? Okay, the conclusion, which is not set here and which should have been, is that it is you have m, so n are the balls and m are the types. So the solution is n plus m. Oh, and everybody who sees the post can see it. It's m plus n minus 1, choose n minus 1, right? So it's, what did we call? We call it the multiset choice. Okay. So I have some other examples for counting multisets. Okay, and we can, so 10 identical prizes, 20 students with no constraint on the number of prizes a given student gets. So this is balls into bins. There's 200 students, they represent bins, and there's 10 balls, they represent the prizes. And you're throwing these prize balls into the student bins. And well, one way would be that there's a constraint, right? Like a ball cannot be, a given student can only accept one prize, right? So this we know, right? It's just 200 choose 10. But what about without constraints, right? So there is n items placed into the 200 ball types, and this is the donut flavor thing. There's 10 donuts of 200 flavors. So again, you're taking the bit strings of length, which is the sum of those minus 1, the number of balls plus 200 minus 1 type switches, and in the you can write either m minus 1, the number of type switches minus 1, there will be the number of ones in this selection bit string, or number of zeros, whatever is simpler. It's simpler here to write this because it's a smaller number. So it's 200 choose 10, right?
One quick question about one quick question about the with one prize per student. The reason it is 200 choose 10 is because those are 10 identical prizes. Had those 10 prizes not be identical, then it would be a permutation of 210, right? Of 200.
Yes. So now if I thought of these prizes as not identical, then I would multiply this by 10 factorial. Yeah, which would be the same as P 200, right? The number of 10 permutations of 200 set. Because it's basically, well, if you think of this that way, then it's a string of length 10 whose characters are students, and no character can appear twice. So you have 200 choices for the first, 199 for the second, 198, right? So it's this 200 choose 10 times 10 factorial, which is the same as 200 factorial over 190 factorial. Okay. Oh, boom, sorry. And I have this on the slide, which is the answer to exactly what we were just talking about, right? And okay, and what if my prices are different and now there is no constraints? Then we're sort of in the simplest case, right? But sometimes the simplest is hard to see once you made all this complicated stuff, right? So this is, again, now all 4 quadrants of this diagram I had at the beginning, right? So the diagram being this one, right? So I have these places, and this one, you know, should by all means already be occupied by the general formula that we just talked about, right? M plus n minus 1, choose n, or m minus 1, same thing. Okay, good. So here is some application of this that is not immediate. How many solutions are there to some equation over integers where the constraint is that all of them have to be non-negative? And you can see that this was similar, because when I started talking about like the different selections, I said, well, there are like 3. Each selection is how many of chocolate, how many of glaze, how many of jelly, and how many of maple, such that they sum up to 12, but they have to be non-negative, right? Between 0 and 12. And it's not so obvious how to count, but there is actually one-to-one between these 2 different things, right? Because I can count the number of solutions to such equations, thinking of them as balls into bins. 12 is 12 units. They have to throw into these 4 bins. Each unit has to be somewhere, and all 12 have to be thrown. This is exactly like selecting 12 donuts from 4 different flavors, right? So these are the so these are the possible selections. But anyway, this is the answer, right? Because it's exactly the same issue. Okay. So how about I modify these problems by asking, so I'm reading chat and people say, oh, how about this way? How about that way? So because I'm a little bit racing, so I cannot quite engage, but by all means, you know, think about this and post it, you know, as a question, and, you know, hash it out on Piazza is a good place. Lower bounds. So how about I get like an extra constraints here? So let's say you're choosing 12 donuts from the same set of 4 flavors, but now you have a constraint that, let's say at least 12 have to be chocolate. Well, that's kind of easy. So just fix those, at least 2 have to be chocolate. So fix those 2 to be chocolate. So that's not really choice. The remaining 10 are chosen without these constraints, right? So that's it. Like the solution to this is just the original question, but with modified variable. You're really choosing only 10 donuts. The 2 already chosen, you know, a priori, right? Sorry about the messed up thing, but I will fix it on the final one, right? But it's just the same question. It's a multiset. Out of 10, I choose 4. I choose 10 donuts of 4 types now. Okay, I'll fix the way it prints on the slides I post. Okay. So the same thing goes for this kind of lower bounds for the number of solutions. I can say, well, how about the number of solutions to this? But all those have to be non-negative. And moreover, I have a constraint that x2 is at least 1, and x4 is at least 3. Okay, this generalizes, right? I just basically I kick out 1 unity and to satisfy this constraint, and 3 unities to satisfy this. I have 8 unities left and unconstrained now. right? Okay, this is terrible again, the layout here, so I'll fix this, but the one ball is no choice, and the three balls went here with no choice, and now I have an unconstrained problem with reduced number.
Why is it 4 bins though? Should it be 2? Because like you already have x2 and x4. Should it just be x2 and x3 you're trying to get, or you have to get them all together because it's 4 bins and 4 variables, 4 bins?
It's 4 variables, 4 bins, because so if you will, the unconstrained one is, let's change these variables. Consider x2 prime, which is x2 minus 1, and x4 prime, which is x4 minus 3. So think of this equation as involving x2 prime and x4 prime, and they sum up to 8. Because you used 4 unities to satisfy these constraints. That x2 has to, x2 prime has to be 1, x2 is 1 plus x2 prime. x2 prime can be anything, but x2 is 1 plus that. And now x2 prime is just non-negative again, without this additional constraint. And when you think of x4 as 3 plus x4 prime, x4 prime is unconstrained, it's just non-negative. And in order to move to this new type of equation, you have used 4 unities, yeah, for these fixed ones. So it's just basically you took your donut, so you placed with like an automaton, 1 donut into x2 bin and 3 donuts into x4 bin, and from now on, it's a fresh game, but with only 8 donuts left. So the solution is like to the original problem with just modified 8 number of balls to choose that can go anywhere, right? So this is the solution for it. Well, what if you had like this funny thing that at least 2 in each bin? Well, okay, so this is the same thing, right? So if you have this at least two in each bin, then I place these 2 in each bin. There's no choices, and now I have the remaining. I have to basically remove the balls I already placed from the 3 balls. Okay, so now how many ways there are of placing 4 balls into 4 bins? And it's 7 choose 3, sure. Okay, very good. How many ways to distribute 15 chocolates to 5 kids? So you have 15 balls, but they have to fall into the 5 kid bins, but each kid gets 1 at least. Okay, so basically I take 5 the chocolate balls, already get rid of them, give 1 to each kid, and from then on I have 10 unconstrained balls, right? So it's the original problem with just 10 balls. And because there's 5 kids, so it's 10 plus 5 minus 1 over 5 minus 1. How many ways to select 12 donuts from 4 varieties? But with an added constraint now that is an upper bound, that I cannot choose more than 5 chocolate donuts because they're not available. Like the guys are just out of them, they have only 5 left. I can choose from 0 to 5 of those, but that's it. I cannot go further. This is tricky unless you do by complement. So sorry about this layout, but the number of ways to select 12 donuts with this constraint, that there is at most 5 now. The previous constraints were at least, and they were easy to deal with. They were like the original problem with the reduced number of balls. But what if you have an upper bound? You cannot go more than 5. Well, then it's unconstrained minus the complement of the set, which is all those that have that do not have less than 5. And what does it mean that they do not have less or equal to 5? Well, they had 6 or more, right? So this just means that the complement is that all the choices that have 6 or more, and we already know how to count those, right? This is the lower bound problem, right? So that there is at least 6 chocolate. So this number, so the total answer is, okay, how many unconstrained selections there are? 12 balls into 4 bins. 12 identical balls into 4 bins. So this is the answer, right? And now you subtract all those that are in the complement of the set you want. So these are that 6, at least 6 are chocolate. So this is, you're basically wasting six of these 12 balls, right? You're placing them on a chocolate bin, and now you have only 6 balls left. And those 6 can fall anywhere. So this is the unconstrained problem with 6 remaining balls, right? So you compute these, whatever, right? But I mean, you don't have to. In fact, okay, so how should you give these in your homework and test? You can give them this way, or you can compute and give them that this is, you know, this is 15, choose 3, and this is 9, choose 3.
Where do you get the 6 from?
6, because I had original 12 balls, and I removed 6 because the 6 had to fall into this chocolate bin with no choices. I had no choice there. I had to fill up 6 slots in the chocolate bin with 6 balls. So I just removed 6 balls from here because they were, you know, used to satisfy this constraint. From then on, this is, you know, this problem, right, is that choose the remaining 6 of any 4, right? So it's this part. Choose remaining 6 out of 4 kind. That's the answer to this. Right. This is an answer to that. Okay.
Okay, so the reason it's 6 is because like you're taking a complement.
Because 12 minus 6 is 6.
Okay.
Yeah, because I have 12 balls and I had to waste 6 out of them to satisfy this constraint of the chocolate being at least 6.
Okay.
Okay. Okay, so, you know, another example. So there is 75 varieties of toffee. This girl selects 12, but some toffees are limited, right? So this is the same thing, right? So you take all the ways of selecting toffees, 12 toffees from 75 varieties. So throwing 12 balls into 75 bins, with balls being the same, and removing all those that do not satisfy this constraint, right? Which is that at least 8 balls were placed in the strawberry bin. And these are easy to count because this is, well, okay, so you took out of these 12 balls, 8 were wasted on the strawberry bin. Now you're left with 4 bins, well, 4 balls that unconstrained can be thrown anywhere in the 75 bins. So this one is 12 plus 75 minus 1. Choose 75 minus 1. And this one, because you removed the number of balls from 12, you wasted 8, 4 are only unconstrained 1. So the answer to this is this quantity. Okay. So listen, maybe I have more stuff. I don't remember, but I think, yeah, so I have some more like of these like sort of general ways, but you know what? I think everybody is tired by now. So I will, if there is much that is still uncovered, I can think at least of one thing that I haven't talked about. I will record an extra lecture and place it, because the sooner you do it, the better. You will have homework, and this final week should be, used on some more forward-looking stuff. So I will just do the record for stuff I haven't managed to cover. There is not so much of that. Okay, and let me now open for questions.
Hi, Professor. Can you go back to the problem with
which one?
The 20 choose 4, I think.
This.
That was like an hour ago. Yeah.
Oh wait, 20 choose 4.
There were 5 people, each having 4 tasks.
Oh, students.
Yeah.
Okay.
I was the one who asked the question on that. Yeah.
Okay.
I just wanted to like.
Wait.
I was wondering if you could explain. Yeah, sure.
Sorry. Where were the students? No. Where they have the students? It was not a complement. It was not here. Where do I have the students? I remember how I had the students, but was it by complement?
I think it's before all these.
But how it could be? Hold on. Oh. Okay. Oh, right. Okay, I found the slide. Sorry, just search students from the. Let me do this. Where is the? Okay, good. So yes. So here is the slide, right?
Right.
What's your question?
Oh, essentially, can you explain again, like for the answer, how do you get the bottom part of the denominator? I mean, for like from my understanding, right? The 20 factorial pretty much means all the possibilities of how like all the different tasks are assigned, right?
Well, so the way I'm thinking of these assignments is that I represent them with a string of length 20. And the characters of that string are digits from alphabet 1, 2, 3, 4, 5.
Yes.
Okay, so this digit says each character, there's 20 characters. First character tells me which student is doing task 1. And the character, either 1, 2, or 3, 4, 5, right, in that place tells me with the student. And the second character is the student who does the second task, and so forth, right?
Right.
So I'm counting strings of length 20 that have these characters, but the characters are constrained in a sort of unusual way, right? So we didn't think of this kind of constraints before, really, where I said that I have exactly 4 ones in the string. So the number of ones is exactly 4. And the number of 2s is exactly 4, and the number of 3s are exactly 4, and the number of 4s is exactly 4, right? So the only thing is their placement, but I have no choice as to how many ones occur in the string. So one way of thinking about this is that you pretend that all those tokens are independent. You'd have this set of tokens. There's 20 tokens, and you pretend you mark them as individual tokens, even though they are, 4 tokens are ones, and they're all the same, right? But let's say on an obverse of a token, you wrote unique ID. So now you think of all these tokens as independent. So how many ways of creating a string out of these 20 independent tokens? It's 20 factorial, right? Because you're just permuting these tokens.
Okay.
But now you have to stop pretending that they are all independent. And how do you stop? It's a K-to-1 rule.
What do you mean by independent?
Independent meaning like indistinguishable, that they're all different, that they are unique.
The 20 tasks are unique, right?
Huh?
The 20 tasks are unique.
No. No, that's completely different. So, no, I'm thinking, okay, I continue thinking of this way. The positions in the string, the index is the task. The character is a student. So the encoding of a choice here is a string where a position in the string corresponds to a task, and a character in the string corresponds to who is going to do the task.
Right.
Now, I could perhaps think of this in a flip way, that there is some string where the position is a student and the character is the task that the student gets. And perhaps this will get me somewhere. Perhaps I can count this stuff. I do not know. But I'm not counting them this way now. Okay, the characters are students, positions are tasks. Okay, so there's 20 positions because there's 20 tasks. So the string has to have length 20. And what are the constraints on the characters in the string? It's these constraints.
Is it 1 to 5? Yeah.
Yes, there's 5 different alphabet symbols, and each of these symbols have to appear with the same number of times in the string.
I thought a maximum of, wait, they all have to be like an amount of 4, right?
Well, because the constraint said that each student gets the same number of tasks. Because 20 tasks and 5 students, so now you know that each has to get 4 tasks. So if that's how you think of a choice, so there's a string where position is a task and a character at that position is the student, then you know that the student has to appear 4 times. Every student, which is 1, 2, 3, 4, 5, has to appear 4 times in the string.
Makes sense.
Okay. Yes. Okay. Great. Thanks. It's very easy to get like are these positions, are these characters, what the constraints are, and the worst thing is to get confused in the middle, right? Like you start with thinking that the positions are tasks, characters are students, and then you switch at some point, and of course it's incoherent. Or
I'm just a bit confused.
But just follow one way and think this through and see if you can do it. And then also, unfortunately, have the ability to say, okay, this is too hard. Let me try to do another way. Okay.
Yeah, I very much gave the 20 choose 4 and then 16 choose 4, the multiplication one, right?
Mm-hmm.
I was just a bit confused about, what 4 factorial represents, if that makes sense.
I think you're talking about this, right? Like that basically I can.
I mean, these all made sense.
Right, but this basically, when you cross multiply stuff, it turns out to look like this at the end. So I don't have to think of them as 11 choose 4 and then 7 choose 4 and then 3 choose 2. I can just think of them as 11 factorial divided by this. And this was this K to 1 rule that also told me that I should indeed take all of permutations of all of them as if they were all unique, these letters.
So essentially it's just
tokens.
It's just a simplification of,
yeah,
the entire expansion of
just
the formula.
That this and this cancels, this and this cancels.
Yeah, now it makes sense now. Yeah.
Okay.
Yeah, that's all I have. Thank you very much.
Yeah, you're welcome. Any more questions?
Professor, can you talk about the question where there are 10 different prices and there are 200 students?
Do you remember where that was?
I think it's sorry, I don't remember.
Do you remember? So the numbers were 200?
Yes, 200 students and 10 different prices.
Okay.
It's a slide that.
Okay, this
like,
one. This one?
Yeah. The last one, yeah. So why is the last one not 10 to the 200th power?
10 to 200. Okay.
Because each student have like 10 choices, and there are 200 students.
No. There's 10 prices means that there's a budget of 10. There's each student doesn't have really a choice, because that would mean that each 200 students cannot get all a prize. Only 10 students can get a prize in total. You see? If
I mean, is there no restriction or any restriction?
Hold on. Hold on, 10 different prizes, 200 students. No, so okay, so wait, I have 10 prizes and 200 students. So what are my selections? I have to decide whom to give the first prize. I have 200 choices, right?
Yes.
And then I have to decide whom to give the second prize, because all the prizes are different. So, and there's no constraints. So independently, I choose who the second prize goes to, and I have 200 choices. So it's 200 times 200. For every prize, I multiply my number of possibilities by a factor of 200, because every prize means 200 choices of who gets that prize. So if you compute, this is going to be 200 in the base, and how many times it's multiplied? It's 10 times, because it's 10 prizes, right?
Yeah, I see. So like the first number prices, there cannot be like 2 students get the same price, right?
Say this again.
So like a number, the 10 different prices, like number 1, number 2 to number 10.
This one?
No, the last question. Last question. Yeah. So I number the prices from 1 to 10. So there is no possibility that like 2 different students, they get the same price for example, the number one price.
No, yes, right, no. So the semantics here is that a prize is a ball that is thrown into some bin, and it can be only thrown into one bin.
Yeah, so only one student can.
Yes, it's like an object, you know, that you can give that object to one person only. You cannot give the same exact thing to two people. Yeah, it's like a ball that has to fall in some bin. It cannot, the same ball cannot fall into two different bins because it's one physical object. So that's what we mean here by prizes, that there are, you know, 10 prizes. Yes, we mean it's like a, you know, it's a diploma, and there's only 10 of these diplomas. So you have to distribute them somehow, but you cannot give the same diploma to two. Yeah.
Yeah, because I face some problems that there is like a prize which can have like 10 people to have it. So
yes.
I think about this possibility.
Yes, right. So yes, so this semantics is very important. It completely changes what the problem is, right? But yes. So this completely changes what the semantics is. So sometimes, well, so sometimes with some of the semantics, it's like it's meaningless. You know, if you can multiply prices, then you know, it could be that there is no, that the whole question makes no sense, what, you know, at all. But here I think it would 10 different prices, and there's yeah, okay, I guess yes, it's a different counting problem.
Okay, that makes sense.
Yeah.
Yes, thank you.
Hey, you're welcome. Is there some other question?
Hi, Professor. I had a question on the homework.
Which
one was it? Sorry, should have had this ready.
You know what? Maybe I will stop recording now. Hold on a second.
Okay.
Stop.